And if you look at the surrounding conferences and research and so on, I can give you on the top of tip that there are very good conferences and journals on design, but the research going on testing is approximately 3-4 times higher. So we have International Test Conference, India Test Conference, Asian Test Conference, we have Global Test Conference, European Test Conference. So these all are VLSI test conferences. I'm just giving you the glimpses so that somehow if you are inclined, you can put your papers there. Now coming to that, why this much boom of testing? Why people are very much? So I would say that is in pure Hindi, if I say it is anivarya anist. Nobody love, but nobody can avoid it. So if you look at it, when you purchase a mobile, I'm just giving, because it's within 1.5 hours, I will not be trying to make the entire testing covered. But I'm just trying, it's an informal way, I'm trying to put some of the words in front of you. So if you look at the general person, our neighbor, or anyone who is not an electronic fellow or anyone, if they are going to purchase a laptop or a mobile, how would they look at it? They would simply see which are the features, which are the functionalities. They are never worried about the testing, how much testing the device has gone with. So for them, testing doesn't matter anymore. So when I ask my student, do you pay any money for testing? They will immediately say, no. We don't pay any single rupee for testing. We pay for design. We pay for functionality. Then I immediately say, all of you are absolutely wrong. Why, madam? How so? I said, you tell me how many of you would like to have the Apple mobile and how many of you would like to have any local China-made mobile. So immediately everyone will be ready with Apple mobile. And then I'll say, how much is the difference of cost? So huge amount of it. Then I say, then tell me what is the difference in functionality. Hardly a few. If you take any Apple mobile, if you take any, I'm not going to have any bad comment on China, but if that's a general term we are using. So if it's a China-made mobile, and if it's a Apple mobile or any higher-end mobile, functionalities are almost similar. Yes? Then what extra amount we are paying for? We are paying for branding. And the branding comes from where? The trust. And the trust comes from where? The user directly putting any single rupee saying that मैं तो टेस्टिंग अच्छा किया है तो मैं 2,000 ज़्यादा दूंगा नहीं, but वो आराम से देते 20,000 ज़्यादा देते. So this is the importance of testing, and it is there everywhere in the world. So again I am saying it is anivarya anist. In which sense? One thing, user don't appreciate, उनको पता ही नहीं है कि मैं किसका पैसा दे रहा हूँ. Then there is a design house. The design house will have a product ready today and it would like to put in market tomorrow. They don't want to spend any single moment for testing because it is a hurdle for them between that to market. Today the product is ready, tomorrow they want to get revenue. And now if you say, I will have to test it for 1 week and then you put it in market and technically it will not chala jayega. So the revenue don't lie. Then what about the designer himself? None of the designers will like that any verification or testing engineer find out some bug in its design and just criticize. So in totality, no one loved it. Only I loved it. Okay. So this is what the scenario of testing. Now, being said so, before I continue, so please take it as an informal discussion and interrupt me at any moment of time. Rather than lecturing, I would like to be more in discussion. It should be dialogue. So please feel free to, okay, with whatever my capacity, I will try to answer, or we can come to a conclusion with this answer need to be found out. Okay, so now this testing is, as I said, it's an honest, it's an unavoidable thing. Designer people are crazy about the autonomous car. Yeah, it's autonomous car. Now you must have heard some news that any autonomous car is having more than 25 or 50 ICs in it. 50 controller लगते हैं उसमें, and so electronic components लगते हैं. Now we think of it कि if your device means IC is not tested properly, and then there is a word that the failure per million, parts per million, failure in parts per million. This is the probability of failing the device. Now, if let's assume that all IC vendors says that out of 100, the probability of my IC will fail is 1. And so every IC vendor has the same policy that we are giving you the guarantee about 99% perfection, we have 1% failure possible. With that, if you are putting in your autonomous car with 100 ICs or 200 ICs, you are making the autonomous car. What is the probability of failing that autonomous car? 100%. Because you have hundreds ICs and everyone is giving that 1 out of 100 the probability of failure. Now at least 1 IC out of your 100 will going to fail. So your autonomous car is going to fail with the 100% possibility. How would this survive? The world cannot survive like this. So if they want that their autonomous car, I am just taking this example only for their autonomous car is to be a failure of 1 per million, and that's what they would like, because when you are in autonomous car you would not like to danger your life. So you want the scenario that perfection is 1 part per million. Now if you have 100 IC and you are asking 1 per million in a car, what should be from the IC vendor? It should be 1 by 100 per million. I am able to draw the picture what I want to show you. And if this is the need, how crucial your verification and testing must be. So either anyone like or not, but this is the demand. In design you can say that I have 1 feature less, so people may not bother. Say okay, वो feature हमें नहीं चाहिए, तो हमें आपका IC acceptable है. But you say that की probability है कि वो तो 10 में से 1 ही चलेगी. अब चाहे आपके पास 50 एक्स्ट्रा अच्छे फीचर्स हो, your product is not going to be sold. Agree? So this is where the importance of testing and verification in general it is. Now we are going to discuss the complete design flow where the testing and verification fits into design flow. कहाँ पे कौन सा verification? Before that, let me just understand the diversity of the group. How many of you are having some courses of VLSI somewhere in the BTech, MTech, PhD, anytime? ऐसा कोई है जिसको VLSI बिल्कुल पता नहीं? हो सकते हैं ना? Okay, 1. So बाकी लोग CMOS IC design से familiar है. सारे को. The words like RTL and gate level and everything is known, most of all. So what I will do, I will. So what do you want to? Should I go a basic level, or I should talk a very advanced of testing, and then the basic of us may not be in the sync. So should I go with the initial basic things and all the words how they fit in the design flow? Is it accepted? So now, whenever there will be, there are a few terms. May I use this word? started एमटेक स्टूडेंट आप लोग अभी यहाँ के एमटेक स्टूडेंट और आप सब पढ़ रहे हैं बीटेक स्टूडेंट आप सब पढ़ रहे हैं. So now there are few words that if you we will talk in terms of design also, but there are one thing is design, then there is manufacturing, and there is ATMP or they call OSAT. So these are the basic words in terms of PLSI. Okay. Now, if I look at the word today, PLSI design means we start from specification and we move to GDS to file where our layout is ready, and we give the layout to the web. So is this a known thing? So we will have verification testing somewhere here also. So here I would say that it is from spec to GDS to file, and this will be done with your all EDA tools. Use cadence or mental graphics or synopsis or whichever tools you are comfortable with and you are available with. After this, it goes to fab, and this is a fabrication, but we call in general it's a fab. So it goes to fab, the fab fabricates it, and then it goes to ATMP. What is ATMP? So ATMP is also, so most of you must have heard that the Micron is coming in India. So Micron is not right now going to open their manufacturing fab. They are going to have the ATMP unit here. ATMP unit is assembly, test, marking, and packaging. So this is how they do. So एक design house है वो design करेगा. After completion of design, it will go to the fab. The fab will fabricate. Again the wafer. Within the wafer there will be number of dies already together fabricated. So the wafer will go to ATMP. Then they will do assembling, test, cut करेंगे, उसको wire bonding करेंगे, क्योंकि जो chip silicon chip is need to be cut, and then there must be wire bonding. It's a golden wire bonding to the package and so on. So assembly करेंगे, test करेंगे, marking करेंगे, and final package करके the world sell करेंगे. उसका एक अगर जो है वो है outsourced semiconductor assembly and test. So OSAT is outsourced semiconductor assembly and test. So इतने अलग अलग टाइप के इंडस्ट्रीज PLSI में होते हैं. Okay. Now, what I am looking at, when I look at, we should have from so there are few companies. There are few companies which are purely a design company, like Qualcomm. They only design, but they don't manufacture and sell. they दूसरों से मैन्युफैक्चर करवा दिए, तीसरे से पैकेज करवा दिए और फिर वो आगे बढ़े. तो एक और कुछ है जो कंप्लीट, उसको हम आईडीएम बोलते हैं, इंटीग्रेटेड डिवाइस मैन्युफैक्चरिंग. सो आईडीएम लाइक इंटेल सब कुछ करता है, डिजाइन भी खुद करेगा, फैब्रिक उनकी खुद की फैब्रिक है, पैकेज भी करेगा और मैन्युफैक्चरिंग भी करेगा. तो इंटेल का खुद का प्रोसेसर भी मार्केट में है. तो दिस इज लाइक आईडीएम. I'm just giving you the words, maybe very crazy and today आजकल जो न्यूज़ में आ रहे हैं, तो I thought कि let me discuss it with you. I hope you are not getting bored कि कुछ नया नहीं आ रहा है और पुराना हम सब कुछ कर चुके हैं. Nothing like that, ना? Please feel free, I can keep on making go next. So IDM companies जो होती हैं, उनके पास पूरा setup starting from the specification to product market में जाने के बाद sales भी करते हैं और पूरा. So that is IDM, like Intel है, टेक्सास है, माइक्रोन है, माइक्रोन का भी खुद का फ्रॉम एंड टू एंड पूरा सॉल्यूशन है. सो दिस आर देयर. बट हाँ, माइक्रोन का खुद का एंड टू एंड है, बट वो जो इंडिया में अभी करेगी वो ये एटीएमपी करेगी. बट उनका हैदराबाद में डिजाइन हाउस है, गुजरात में वो एटीएमपी करेगी और फिर तो उनका पूरा बाहर है. तो बट दे हैव. तो अभी मैं ये बोलना चाहती हूँ कि माइक्रोन यहाँ पे बड़ी आईटी कोर कंपनी कौन सी है? Anyone? ARM. ARM never do anything. They just use the brain, prepare the IP code, the design, intellectual property, and then they sell it to processor for design. So, एक होती है IP core companies, फिर होती है EDA tools company, जैसे Cadence, Synopsys, Mentor, वो सारी फिर आपको tools provide करती है. तो ये डिजाइन हाउस को वो दोनों लगेंगे, डिजाइन हाउस को दोनों लगेंगे, वो IP core से IP लेंगे, EDA टूल वालों से EDA लेंगे. Intellectual property code. Okay. So now the design houses, which are say like Qualcomm or so, उनको अगर कोई प्रोसेसर बनाना है तो ARM से प्रोसेसर के IPs लेंगे, फिर EDA टूल से उनका EDA टूल्स लेंगे, उसके बेस पे वो अपना खुद का इंटेलिजेंस यूज करके बनाएंगे. Then it will go to fab. Now there are few companies purely in fab, like TSMC and few others. In Taiwan is the major hub for all manufacturing things. So they don't have their own design. They just take the design from someone, fabricate, and give the wafers there. Now there are two options. Some of the fab companies, they provide you that ATMP services also. They also assemble, test, mark, and pay for you. But you can have the other option also. I want to get you fabrication from you only, and then there are purely ATMP players. वो fab नहीं चलाते हैं, वो सिर्फ पैकेजिंग चलाते हैं. So you can give to them also. आपकी ready wafers आप उनको देके कट करवा के पैकेज करवा सकते हैं. So this is how this the complete flow is all about. So anything here? Any discussion? Now if I go through, so every step there will be a number of steps in design, there will be a number of steps in manufacturing, फिर ATMP में भी बहुत सारे steps होंगे. So your thought as a specification, your requirement will go to the number of forward steps and will become a product and will be in market. Now each step towards the market, you will have to check that whether my step is right or wrong. Because if step गलत direction में ले लिया तो your product will be of no use. So now I want to have a complete picture. You have idea that one day one fellow hired कि okay, I want to have a graphical processor. उसमें मुझे ऐसा कुछ image processing करना है, उसके लिए मुझे ऐसा कुछ hardware चाहिए. Now that is the specification, and it went on, and then the graphical processor was written. So it has gone through this entire path. And for every one conversion or every one transformation, you need to have a backward look and make sure that in my path, my step was neutral. And that comes under the umbrella of testing and verification. तो टेस्टिंग एंड वेरिफिकेशन कोई एक जगह पे या एक लेवल पे नहीं होता है, हर एक जगह पे होता है. आपने वेफर फैब्रिकेट कर ली है, now the wafer is properly polished, it has no deformation, it is perfect. That is also a kind of testing. We call it wafer testing. Okay with this? So anything here? Okay. Now if I go with design only, so if I say design, most of you will agree with that. You have first of all the first stage of design is the specification. Agree? After specification, what will be the next step? What will be your next step? Anyone? High level architecture. Okay. Then? Micro architecture. Then? RTL design. Well, anyway, behavioral coding, have you heard about? So, once your architecture is ready, Somewhere you will have to do behavioral coding. Whether it's a macro level or micro level. So can I call it a behavioral? Which language you use for this? Oh, fine. After behavioral, it will be RTL. अगर साइंस की आप यूज करते होंगे तो आप RTL कन्वर्ट करते हैं. Okay. This is for RTL. RTL के बाद आपको क्या करना चाहिए? Synthesis. Synthesis is a process. But what will come up as a result of synthesis? Netlist. So it will be gate level netlist. After gate level netlist, if you again synthesize, it will become transistor level because all gates are made up of transistors. Circuit level or transistor level. Because circuit is what? Transistors are in C. If you put all together, it's a circuit. Inductor is generally we don't use in DLS, right? So for us it is RC and transistor. So either you want to get the transistor level netlist or circuit level netlist. After transistor level, what you make out of this is layout. You know that each transistor is made up of source, drain, gate, अलग-अलग doping, अलग-अलग polysilicon, sorry, अलग-अलग metal, and then polysilicon. So now basically it's a physical layout according to the transistor. So is this flow understood? Now we will have to see within this flow also how we will make sure that the next step is not the wrong step. When I convert my specific behavior to RTL, again the RTL should adhere to specification. It should not move away from the specification. So every time I will have to make sure that even my transistor level netlist is not moving away from what I was requiring later and up transistor level पे जाके वो multiplier बन गया है. Every time I will have to convert, and that comes under the testing and verification course. Okay. Now, so we will go hand to hand with this flow because ये है तो हम testing verification करेंगे. इसका नहीं करेंगे. ठीक है? Let's understand how this thing, your behavioral coding and RTL coding will be different. How this two will be different. Any guess? Both the words are known to most of us.
Yeah. Behavioral coding can be synthesizable or cannot be synthesizable, but RTL coding is synthesizable.
Perfectly. But why it is?
Because behavioral coding includes many constructs which are used for verification only, and those constructs are non-synthesizable.
Okay. What is RTL exactly? Resistor transfer logic. Now let's understand these two words properly. If I ask you, let me take a very simple example. कि मेरा तो सीधा साधा इतना जरूरी है कि मुझे दो नंबर से उसका एडिशन करना है. And my numbers are decimal from 0 to 19. So this is as a non-engineer layman person, I will ask you कि भाई मुझे एक ऐसा प्रोडक्ट दो कि मेरे पास जो दो नंबर हो 0 to 99 का उसका मुझे समेशन करके दे. ऐसा मुझे डिवाइस प्रिपेयर करके. So my specification right now I'm not going in timing or power वो सब बाद में. So if my specification says that the summation of two numbers which are 0 to 99. Now 0 to 99 are integers number. Okay. Now if you write down your very low code with this, you can say that A is int 0 to 99, B is int 0 to 99, and C is your sum is equal to A plus B. Okay. And then you simulate. You will be able to give A 0 to 99 anything. In integer only you can. In B also. Now, is this design has anything to do with hardware? No. It is purely behavioral. The way you describe in your normal language. Now, when you describe something in your normal language, it can be converted into hardware. It cannot be converted. synthesizable, cannot be synthesizable. I can say that A should come after 5 hours. A should be high, 5 hours after B should be high. So I can describe behavioral, but I can have the hardware for it or I cannot have hardware for it. So this is the, but now so this is my behavioral code where I would say that A in 099, B in 099 and sum in 0 to 198. Don't go with syntax wise. मेरे लोग syntax अलग है, but मैं just simplified लिख रही हूँ. Okay. Now if I convert this into RTL, how the RTL will look like? Because I know that now कि any number, कोई भी एप्लीकेशन के लिए आपका सेंसर से कुछ डेटा आता है, आपका इनपुट से कुछ डेटा है, कहीं से कुछ डेटा आता है. Basically it is a number, maybe floating point, maybe integer, कोई भी but number होगा जिसको हम प्रोसेस करते हैं वो ज़्यादातर नंबर होता है. Now this number hardly any possibility that it is represented by a single bit. Single bit में तो 0 और 1 दो ही ऑप्शन है. तो जो भी आपका नंबर आएगा, it will be a multi-bit number, more than 1 bit. Every 99.999% it will require in digital domain, if you want to code it, it will require more than 1 bit. Yes, agree? Now if I want to code a number into more than 1 bit, what it requires? A group of bits, and a group of bits means a group of D flip-flop, and that is called register. So now we are moving to register. I'm not sure whether you have think of RTL with this clarity or not, but RTL, what is known to everyone of VLSI RTL. But when I ask in a general group, what RTL do you mean by? I am not getting the exact answer what I want to have the precision here. So now if I say that 0 to 99, I want to put it in hardware, I will require a register. क्योंकि अब मैं उसको डिजिटाइज करूँगी, बिटवाइज करूँगी, कितने बिट का नंबर बनेगा ये? 8 बिट का. So then it will be a जो भी है 0 to 7 register A. ठीक है? 8 bit. Similarly, register B. And then I will have to put now यहाँ पे जो मेरा एडर था, वो तो एक मैथमेटिकल फंक्शन था. वो जो मैथमेटिकल फंक्शन अरिथमेटिक, वो प्लस को कोई हार्डवेयर से लेना देना नहीं था. वो सिंपली आप जैसे मैटलैब में या जैसे कहीं पे भी करते हो, it has nothing to do. But now it is to be converted into a physical hardware adder. So this is an add math function. Now it becomes adder, hardware adder. You can take any kind of hardware adder to bring it upon your choice. And then I will have sum. And if this is 7 bit, if I assume it is 7 bit, this will be of 8 bit, then it will be 9. And then the data will transfer from here to here, and here to here, and here to here. That is why it is called register, transfer. And because now everything is in hardware, it is 100% synthesizable. So, any question here? I hope it's not boring. No. Now if I convert, because this is a D flip-flop, If I convert this, everything will be of gate. If I convert this, everything will be of gate. So I can transform this entire circuit into corresponding gate level netlist. हर एक का अपना अपना गेट वर्जन हो जाएगा. And फिर each gate is made up of transistors. तो वो पूरा का पूरा हम ट्रांजिस्टर सब गेट को अगर उसका इक्विवेलेंट ट्रांजिस्टर डाल देंगे तो ट्रांजिस्टर नेटलिस्ट हो जाएगा. और फिर एवरी ट्रांजिस्टर इफ आई कन्वर्ट इट इनटू लेआउट, उसका सोर्स, ड्रेन, गेट, the peripheral area, then it's there. So now I want to understand what is this netlist means? Netlist क्या है? How we will define the word netlist? Because electronic engineer from perhaps second semester itself they start working about netlist. Everyone of us? How we define netlist? What is it? Okay, correct information of
gates present in the design and their interconnection.
Okay, perfect.
How the gates are connected in.
So how does it different from your schematic? अब schematic ड्रॉ करते हो ना, थर्ड सेमेस्टर बीटेक में डिजिटल लॉजिक डिजाइन के कोर्स में सारे लोग schematic ड्रॉ करते हैं. तो schematic से नेटलिस्ट कैसे निकलता है? Because your schematic also goes with the definition only. It contains the gates and interconnects, how they are connected. So that is in schematic also. Because I am targeting the BTech students as well, I am enjoying to ask you more questions. How your schematic and netlist is different? There is no difference content-wise.
Pictorial. It is pictorial while the netlist is written text.
Because you want to have it processed by some automation tool, some software code. The software code cannot go with individual schematic, because if you draw a schematic for a given circuit, he will draw something else and you will draw something else. He will put and get here and or get here and then draw a straight line and you will make a fancy routing. So for EDA tool, it is now it becomes a image processing problem rather than working on the circuit. But if both of you are describing it, you will say that gate A and gate B is connected with a wire called C. And then there is no ambiguity. So netlist is a textual information, and if I give you a format कि नहीं सबको netlist एक साथ ही लिखना है कि पहले नेम लिखना है फिर उसके बाद वो इनपुट है आउटपुट है या वायर है क्या लिखना है. So if I give you a format to everyone across the world, if the circuits are similar, their netlist will be similar because they will follow the standard format. But for pictorial information, you cannot guarantee. कोई गेट में हरा रंग भरेगा और कोई गेट में नीला रंग भरेगा. So then also the EDA tool will be confused. So जहाँ तक हो सके. Now layout level पे भी आप जो layout के बाद GDS2 फाइल बनाते हो, that is a netlist code. Layout आप schematic draw करते हो, that's a visual thing. But if you convert it, it will be again a textual information which goes to pair. Okay, so this is our design for any question here? Yeah? That's why I'm coming, but the design. Because I will say you will have to verify the netlist. I want to make it confirm that you are verifying netlist. So is this fine? Now, if we start with discussing the specification हम verify करते हैं, वो बहुत higher level पे इंटेलिजेंट, उसके लिए कोई automation नहीं लगता है कि भाई आपको ये काम करने के लिए हमने जो specification बनाए हैं वो सही है. So that is a purely work of intelligence, a manual work done by a very experienced people of the team. So there is no first step is without any verification towards wherever we have to step. So मान लो if you have written the behavioral code, you are doing the first thing is you must be simulating it. How you simulate? You Verito code, you open it in simulator and force the value. A is 55 and B is 45 and manually you check the answer. So that is the first step of verification. Okay. But if you have, suppose if you need to verify a 64-bit adder, 64-bit adder. So how many input combinations you will have to apply for verification? 64. No. What do you understand by a definition for 64-bit adder? उसमें input कितने होंगे? 128 A और B के और एक C है. Because our part when we say it is a 64-bit processor, उसका मतलब क्या हुआ कि वो सारे जो वर्ड्स है वो 64-bit के ले सकता है. मतलब अगर 64-bit adder है तो A is of 64, B is of 64, 4 and 1 C in. So it is a 129. Now so if you want to verify the exhaustive, एक दो चीजों को verify करके हमारा lab का काम चल जाएगा. But actual verification में जो exhaustive verification. So there you will have to apply 2:129 combination. अब आप सोचो कि एक सेकंड के हिसाब से भी आप वेरीफाई करते हो 2:129 into 1 second. सालों के सामने मतलब more than your complete human life. उससे तो ज़्यादा ही है. So you will go with automation and you will write the test case. So कहीं test case writing हुआ है discussion. ये आप सबको तो मैं वो नहीं कर रहा. I will see. Is it fine? So when you are writing a function test bench for behavioral coding, verify it with specification here that is making it is giving 45 and 45 90 answer देता है कि नहीं. So this is called functional behavior. Sorry, functional verification. You can do it manually. This is hardly anyone does in industry. You can do it with test bench. Here also, industry has so many options. They have unified verification methodology. They use reusable verification methodology, RVM. And for most of the things, now the industry has started using another language which is system variable. Why system variable? Because when you are verifying, you are not worried about the hardware part. For functional verification, आपको hardware का कोई problem नहीं. So you can have all the good concepts of object orientation, OOPS fundamentals and also. So आपको class और सब लेके कर सकते हो. तो यहाँ पे people are using system variable. Now once you are done with this, फिर आप यहाँ पहुँच गए आपने this is called synthesis process. जो आपका forward step है उसको process को synthesis. Now once again you have done synthesis, you will have to check this. Now you will not check it with maybe not directly with specification. You can check to earlier also. But okay, for one first time, sorry for that, they will check it with specification. Now here they will not have to check only functionality, but addition to functionality they will have to check timing also. यहाँ पे सिर्फ functionality, because timing आप predict ही नहीं कर सकते हो. आप बोल रहे हो कि A plus B 45 plus 45 90 होना चाहिए. How can you predict about time? FPGA में डालोगे तो कुछ और time होगा, ASIC में कुछ और होगा, microprocessor में कुछ और होगा. So you cannot comment on time at that point of time. But now slowly I am moving toward hardware. build my design in totality adjust to the given time. Because now for each new product, we don't want only the right answer, but we want right answer within the right time as well. जो नया प्रोसेसर आएगा वो ये बोलेगा कि चलो मैं तो अच्छा आउटपुट देता हूँ, बट पुराने वाला 1 गीगाहर्ट्ज चल रहा था तो मैं तो 0.8 गीगाहर्ट्ज पे चलूँगा, बट मैं आंसर सही दे रहा हूँ. Isn't it any use? No. So the new device that comes with its method. We will have not only the function right, but we will have the timing also right. So now onwards, I will have the functionality plus timing. And then there is a good words here. Which one is a dynamic timing being analysis? Or you can have functional verification plus static timing analysis. So these are the two options. Now how these two options are different? So is static timing analysis discussed in this forum and I missed it. So how the static timing analysis will be and what it will do? How it is different from dynamic timing analysis? What exactly the purpose of doing static timing analysis?
Without giving the actual clock, we analyze the timing of the circuit.
But without giving the clock, we analyze the time. But it is then the clock नहीं है, combinational circuit में नहीं हो सकता. Combinational में तो already clock नहीं है. हाँ? So, but then how it is different from the actual dynamic timing analysis? Suppose I have a circuit here. Right now, suppose my circuit is like this. It's a black box. मुझे पता नहीं है कि अंदर क्या है, but मुझे ये पता है कि if I give A, B, C, what my output D should be. वो मेरे पास मॉडल ट्रुथ टेबल है. Now, एक तो मुझे क्या करना है? A, B, C और उसके साथ जो मॉडर्न डी आउटपुट आ रहा है सही आ रहा है कि नहीं वो चेक करना है. और ये जो कॉम्बिनेशन मेरा आउटपुट सही आ रहा है कि नहीं. और दूसरा मुझे उसका टाइमिंग भी चेक करना है कि क्या. For each of the combinations, I will have different timing because it could happen with possible कि सबके लिए एक ही टाइम आएगा. अगर मैं 0 0 0 दे रही हूँ and 1 1 1 दूंगी तो आउटपुट चेंज होने में उनका टाइमिंग अलग हो सकता है. Agreed? Now what I will have to find out that if there are different timings from say suppose TD1 to TD8, I will have to find out the maximum of this. कि कौन से इनपुट के लिए maximum timing लगता है. Yes? And that maximum timing should not go beyond the limit timing. मुझे बोला जा रहा है कि मेरा आउटपुट मैक्सिमम एलाउबल डिले 5 नैनोसेकंड. तो इसमें जो मैक्सिमम है वो 5 नैनोसेकंड से कम होगा. Agreed by all? Now, if I try to do all this thing, हर एक का मैं ATC भी दूँ और D भी चेक करूँ और उसका टाइमिंग भी करूँ, तो जैसे मैंने अभी आपको बोला कि it will become a very time consuming process. और एक छोटा सा है. See, I understand that मैंने भी when we talk about STL, when we talk about functional verification, हम ज़्यादा से ज़्यादा टूल की ही बात करते हैं. ये स्क्रिप्ट रन करो तो ऐसा आउटपुट आता है, वो स्क्रिप्ट रन करो तो ऐसा होता है, ये कंस्ट्रेंट डाल सकते हो। बट मेरा खुद का ये एक्सपीरियंस रहा है कि वो कहीं न कहीं मगा पाता है स्टूडेंट, बस वो प्रोसेस के स्लेव्स बनते हैं। तो वो मैं हमेशा अपने स्टूडेंट्स को बोलती हूँ, you could be master of your DDA, not the slave. But when you go with the menu, पहले ये स्क्रिप्ट लिखो, फिर ये कमांड दो, फिर ये कमांड दो, फिर ये आउटपुट जनरेट होगा, उसके फाइल का नाम ये रखो, फिर वो फाइल को यहाँ इंपोर्ट करो, फिर ऐसे रन करो। At the end you have nothing knowledge. You just know how to run the tool, but tool के पास सारा knowledge है, आपके पास कोई knowledge नहीं। Do you agree with me? आपको कंफर्ट नहीं लगता है कि टूल क्या कर रहा है। So if you know कि what the tool is generating, why it is generating, तब मजा आता है। So suppose now मुझे यहाँ सारे सर्च करने, मान लीजिए 101 है, तो उसका आंसर आना चाहिए 1 आइडिया। And I want to find out कि what time it will be take. What I will have to, is this okay? I am okay about this scenario. Everyone is with me?
Yes.
Ideally, 101 should answer me 1 output, and I want to find out what time it will take. Now to find out that, what I will have to do? Suppose I apply A1, B0, and C also 1, then my D will be 1. But this way I cannot make out what is the delay. So what I will have to do? Somewhere I will have to apply a pair of vector. I will have to apply A0, B0 and C0. If I apply 0, 0, 0, and then I make this one, at the same time if I make this also 1, and after some time this D will become 0 to 1, then only I can find out what is the time for this vector. So do you agree that if I want to take both functionality and time vector, I will require a pair of vectors. We call this input as a vector, S vector. So for 101, I want to find out the time. पहले मुझे उसे उल्टा वो लगाना पड़ेगा, तभी तो उसमें वो ट्रांजिशन आएगा, मैं मेजर। So now if मैंने पहले से ही यही लगा दिया होता तो मैं स्कोप पे मेजर ही नहीं कर पाती कि कब टाइमिंग आ रहा है। So my point is कि in dynamic timing analysis, you can verify function and timing both together. But it is a very complex process because it requires pair of vectors. For every vector, there will be a initialization vector and target vector. अब अभी हमने डिस्कस किया कि एक जिंदगी में नहीं होगा, तो ये तो 2 जिंदगी की बात कर रहे हैं। Any question here? So even though the dynamic timing analysis was golden, it survived जब इंडस्ट्री छोटे डिवाइसेस बनाती थी तब। जैसे ही इंडस्ट्री ने बहुत कॉम्प्लेक्स और नावेडेज अगर आप नया प्रोसेसर बनाते हो तो उसमें आराम से 500-600 इनपुट्स होते हैं, आराम से होते हैं प्राइमरी इनपुट्स क्या करते हैं। So then industry came to the thing that कि भाई फंक्शनल वाले अलग से फंक्शनल करेंगे, जो फंक्शनल करेंगे वो सोचेंगे कि टाइमिंग इज 0, दुनिया में कोई डिले है ही नहीं, तो उन्होंने 2 पार्टीशन कर दिया। और जो स्टैटिक टाइमिंग एनालिसिस करेंगे वो सोचेंगे कि फंक्शनलिटी से हमें कुछ मतलब ही नहीं, इनपुट एंड आउटपुट के जो डिले है उसी से हमें मतलब, अब आउटपुट सही है या गलत वी डोंट माइंड, हमें सिर्फ ये देखना है कि इनपुट लगाया आउटपुट कब, अब आउटपुट सही बदला गलत बदला वो फंक्शनल वाला क्या है। तो मैं ये तो there is 2 separate words existing in industry. So one day we will be doing functional verification, assuming there is no gate delay, no net delay, nothing. Output सही है everything. And the other will be doing static timing analysis. So we are doing verification. Static timing analysis is a part of verification. It's called timing verification. Any doubt here? So now, so most of the time, इंडस्ट्री ने जो टेस्ट बेंच यहाँ पे बनाई बिहेवियरल कोडिंग से ये उसी को थोड़ा मॉडिफाई करके वो ये भी आरटीएल से स्पेसिफिकेशन भी वही करेगा उसी से करेगा एंड दैट इज लाइक ए कॉल इट रीयूजेबल वेरिफिकेशन मेथोडोलॉजी वहाँ पे आपने ए और बी इंटीजर
I'm core device researcher and I work on the working horse of the today's industry. So can you tell me which is the working horse of the today's electronics industry? Yes. It is MOSFET. How many of you heard this word? It is metal oxide semiconductor field effect transistor. So actually this device is the working horse. Why? Because if you see the today's integrated circuits, the ICs particularly are based upon the device. So if you see this MOSFET, this MOSFET play an important role. The reason is it has the planar technology. So today if you see the integrated circuits which we have, all are based upon the silicon, right? These are the silicon ICs. So why is all the ICs are based upon silicon? Any guess? What other material? Semiconductor. Why silicon? Available in bulk. Thermally stable. Actually, this silicon has one work-related property. What is that? Suitable. Actually, if you see the silicon vapor, and the silicon vapor, if you put the silicon vapor in the environment, it will form a native oxide. Why? Gallium arsenide means what? Gallium arsenide is third, fifth semiconductor, yes. Right? If you see third row, third column, fourth column, fifth column, second also will take, and sixth also will take. So what was here? Carbon, silicon, germanium. Right? So people focused on silicon. They started with the carbon. Right? So we have the carbon, na? Carbon means graphite, graphene, carbon nanotube, quantum dot, fluorine. What these are? These are polytypes of, carbon related things, right? But what is the difference between graphite and carbon nanotube or graphene? Lattice structure. These are all the How many of you heard about 3D, 2D, 1D, 0D? Three-dimensional structure, two-dimensional structure, one-dimensional structure, and zero-dimensional structure. Three-dimensional structure means? Three-dimensional structure means X, Y, Z. Right? This X, Y, Z. All these dimensions are more than the D Broglie level. Right? This is 3D. Silicon is the bulk silicon. Right? X, Y, Z dimensions are more than the D Broglie level. We will not talk about the quantum that side, right? I'm just telling you these dimensions are more than that. It is a 3D. Silicon ICs or material. It is a 3D crystal structure, right? Tetrahedral geometry is there. That will be 3D. 2D. 2D means two-dimensional means one of the dimension is lower than the D Broglie level. If one of the dimension is lower than the D Broglie level, it is like a. This is what? This is 3D. What about 2D? Ribbon. Right? Two-dimensional, no? It's like a ribbon. X and Y. Z dimension is lower than the D Broglie ribbon. And when you form this ribbon, it is graphene. So 3D is graphite. 3D is graphite. 2D is graphene. Right? And what I did is this ribbon which I formed, I just wrote it like this. Then what will be forming? A ribbon I wrote like this. This will be forming 1D. Means X, Y. Both the dimensions are lower than the D Broglie level. There will be only one dimension. It will be forming a tube. Carbon nanotube. CNT. So 1D are CNT. It will be like this. Y. One dimension. This X and Y dimensions are lower than the D Broglie level. There is only one dimension. This dimension. Carbon nanotube. If I make this third dimension is also low. Lower than the D Broglie level. X, Y, Z, all the three dimensions are lower than the D Broglie level. Then what will it form? It will be forming a quantum dot, and that is fluorine. So, we do have 3D graphite, graphene, 2D, 1D is carbon nanotube, and the quantum dot is fluorine C60. So, these are the materials people try to develop the devices and the further nano electronics development. Not only this, I told you right, gallium arsenide. These are called as 3-5 semiconductors. So why that will not be possible? Because gallium arsenide is because of toxicity, it is a closed tube process. Silicon is open tube process, right? Gallium arsenide you cannot fabricate. It has high speed because mobility is high, right? So it is high speed. It is the direct bandgap semiconductor. That is what is used for the optoelectronic applications. How many of you, or is anybody who see the silicon LED? Why not? Silicon is the indirect bandgap. Gallium arsenide is the direct bandgap. So LED, how LED works? Continuous emission. Right? Electron will move from the valence to the conduction band to valence band, it will return back. It will radiate the light. photons. It could not be possible in the silicon, because if you see the EK diagram, EK diagram is energy versus momentum, right? So if you see the EK diagram, this is direct band gap, this is conduction band, this is valence band. When electron will move, gallium arsenide is the direct band gap. Silicon is indirect, like this. When it has to move here, it has to first of all lose momentum and then it goes back. So when we lose the momentum, there will be phonons. So we know about electrons, photons. Phonons means vibrations. So when the electron will move from the conduction band to the valence band, first of all it loses the vibrations and then it goes back. So we could not make the optoelectronic devices with the silicon. Now people are trying to use the third field semiconductors. They have developed the SiC, silicon carbide, silicon germanium, not only these, cadmium, sulfide, right, CDS. These are the different materials people are developing, because silicon may be going to die in few years, right? So this is the research people are going for the material sides also. So remember this. So we'll be talking about the device developments, materials, and what other developments happened so far in the device and the material side. So we'll be talking about this IDVD. So this is the linear curve saturation will going to happen, and this is the microelectronics. This person you might be knowing or no, right? So every technology develops after 1.5 years, and as I told you, right, 4-bit processor to the Pentium when we move. These are the developments happen in the Moore's law. Then how far we can scale down? I mean, I already told you, when people talk about 100 nanometer in 2003, after 100 nanometer when we start scaling down, the nano electronics came out, microelectronics and the nano electronics. So we need to have this. Okay. No, I think continue. Okay, so I will just show some couple of slides. So as I talk about the microelectronics and nanoelectronics, I hope it is not boring for you.
No, sir.
If you feel, then tell me, because my goal is to tell you about this physics, right? Instead of just coding the slides, right? Your understanding, the knowledge transfer is most important, right? So I hope you are understanding.
Yes, sir.
So somehow I am going at the basic physics level, but I hope that basics already you know. Okay, we move further. So that is what this scaling was started with. This is the nanoscale transistors I am showing you. These are the original image. So this is INTEL's 2003. This transistors and 6 nanometer MOSFET came up. Then this is the, I mean, these would be the devices. Now when we talk about the small nanometer dimensions, we need to discuss about the quantum effects, because the electrons will not be like a particle, it will move. It will have the quantum confinement effects as well. So we need to study the new physics, that is quantum physics, and we have the effects like leakage, tunneling, quantum scattering. These effects will come up. So this slide is most important. The major hurdle which we do have was the leakage power dissipation. As I told you, when we started scaling down, I mean, you could see here, when the transistor channel length was around 1.5 micrometer, And when these processors came up, the major hurdle was the static power dissipation. When we talk about the CMOS developments, right? So as I told you, CMOS has the low power dissipation. But although it has the low power dissipation, there are two power dissipations in CMOS. One is the static power dissipation, and the second one is the active power dissipation. When we scale down, the static power dissipation, by the way, is go on increasing, and that is mainly because of the leakage. I told you that if you see the transistor structure, or if I plot this ID versus VGS, this is linear scale. This is linear. This is just kind of the quadratic behavior or square law behavior, right? It's like dial characteristics you will see, and the voltage at which it happens is the threshold voltage. So the regions, I mean saturation and the linear regions that already we are studying. So you feel that this is zero. Below VT. Below VT means sub threshold. Sub means below. Sub means factor. Right? Sub means below. Sub threshold. Below threshold. So below threshold is the cutoff. So what we talk about? Cutoff, linear and saturation. But below cutoff, in cutoff region, the ID should be zero. It shows it's zero, but in reality it is not. If I am plotting it in the log scale, log ID, then the graph will be like this. This scale is like decade scale, like semi-log. You might have used this paper, right? Semi-log y-axis. So it is in decade scale. So this is your VT. So below VT, there is this current is called as sub-threshold leakage. This is sub-threshold leakage current. And this current is ion, right? This is the on state drive current. This is ion. And when this device is off, this is I off. So there are two currents, one is ion and I off. Ion means on state drive current, the device is on. Off state means the device is off, below VT, VG 0. Right? So when VG is greater than VT, then device will become on. When VG is lower than VT, the device is off. When device is off, there should not be any current. But in practical, there is some current is flowing. That is the sub-threshold leakage current is flowing. And the slope, if you see, so this decade change, right? This is a decade change, one decade change, and this change is millivolt change. So there will be sub-threshold slope, millivolt per decade is the unit, right? This will be millivolt per decade. So what we wanted at the switch. So this sub-threshold slope will be 0. We wanted still. So by the way, we will be looking for this I on and I off. So our figure of merit is speed and power. So I wanted to increase the speed. So speed is inversely proportional to the intrinsic gate delay, tau. Right? Tau is intrinsic gate delay, and this tau would be equal to Cg into VDD by ion. So if I want to increase the speed, what I need to do? I need to reduce the tau. This tau I have to reduce, intrinsic gate delay I have to reduce. If I want to reduce this tau, I need to reduce this Cg, gate capacitance I have to reduce, or either I have to reduce this VDD, or either I wanted to increase this ion. On state drive current I wanted to increase. When I increase this tau will go down. When tau will go down, my speed will go up. Similarly, this power dissipation particularly would be I off into VDD. So what is my goal? My goal is to reduce this power dissipation. So if I wanted to reduce it, this I off I wanted to reduce. So my second effort would be to reduce the off-state leakage current. Because power dissipation I wanted to reduce. And then why we need the scaling? The reason of scaling is if you see this ion that is IDS in saturation region, this will be half mu n Cox W by L VGS minus VTH square. So what is my goal? My goal is to reduce this down, increase the speed. If you want to increase the speed, this ion is at the denominator. Since ion is at the denominator, I want to improve ion. Right? This ion, if you want to improve, this IDS, I need to improve.
Yes.
If I want to improve this IDS, what would be the probable possibilities with me? The possibility would be this VGS minus VTH difference. This is called as gate overdrive voltage. This difference I wanted to increase. How I could increase the difference? VTH. Reduce VTH. This VT, I will start reducing. If I reduce VT, obviously this difference will increase, and since difference will increase, my ID will go up, ID will go up, my delay will go down, my speed will go up. So this is my first target. VT I wanted to reduce. But when I started reducing VT, my IOP will also go up. Off-state leakage will also go up. Because if I reduce VT, my IOP, these characteristics, this VT if I reduce, let us say VT is here, ion would be improved, this IOP would go up. And since IOP would go up, my power dissipation will go up. So I could not change more VT. Another way is this W I could increase. W I have to increase, that is what in CMOS we might have was fingering. Width, device width, MOSFET width, they start increasing because ion will go to up. What is the other way? L is at the denominator. L is the channel length. Right? This channel length. Channel length we reduce, L will go down. That is what we start doing scaling. As I told you, right? When we do the scaling, integration density not only will improve, it will improve the speed also. That we require. So when we go down from 10 micrometer to 10 nanometer, my ion will go to improve. That is what people started doing scaling. So L will go down means ion will try to improve. Not only this, other parameter which I could have would be Cox. Cox is gate capacitance. So Cox I have to increase or reduce? Cox I want to improve.
Yes.
Cox is what?
Absolutely.
Epsilon ox by Pox. Epsilon ox means what? Permittivity of dielectric. I was using SiO2. SiO2 has the permittivity of 3.7. So I wanted to improve ion. So if I wanted to improve ion, then I'll have to improve the Cox. If I want to improve the Cox, I'll have to improve the epsilon ox. If epsilon ox I want to improve, I'll have to go with the high-K dielectrics. So in the MOSFETs, you might have heard high-K dielectrics people try to use.
Yes.
The high-K dielectrics like HO4. It has a dielectric constant of 22. So Cox will go to improve. Or other option which I do have would be reduce the Tox. Reduce the Tox. When we reduce the Tox means the gate dielectric thickness. This thickness. Reduce this Tox. Right? When we reduce the Tox will improve. What is the other solution for me? Mobility. So I have to, if I want to improve the mobility, I have to use the materials which has the high mobility. And which are those materials? These materials are third-field semiconductors. Gallium arsenide. Gallium arsenide has the higher mobility than the silicon. So when I wanted to make a device or material analysis, if I want to do, I'll have to make such changes. So silicon germanium I'll have to use. I'll have to use gallium arsenide. Right? Or I'll have to look for the other materials to do that. But from IC fabrication point of view, it will be difficult to use gallium arsenide because it is a open tube process. It is a closed tube process, sorry. Right? So people are trying to put the efforts to improve this. And so people try to do this, but at the same time we have to look for the leakage also. And this leakage leads to the heat. Right? Heat sinks. If you see the power dissipation here in terms of the heat, when it was in Pentium around 100, now it reached to the nuclear reactor, and when it reached around nanometer region, it may reach to the nuclear reactor or rocket nozzle also. And when it reaches that, how our processors and our everything will going to work with this. So the current research challenge for the device researchers is the leakage power dissipation, where people are trying to do research to develop this. So that is the major power train now, and you could see here the gate length scaling and the research people did on the gate length, right? So you could see if we change this, you could see the passive power density is changing as we go on changing the gate length. So when we were around 0.01, the power density is increasing. And if you see the processors, when we were on the 4004, this power density was lower than the 10. But when we reach after P6, I4, I6, I7, right? One core, octa-core, then the power dissipation is huge. That will be the major argument. Another question I just wanted to ask you, just for curiosity. Why we go with the dual core, octa-core, hexa-core kind of the processors? Why not single core? Multiple processing. This reason was this power density. I will show you. See, when we talk about the power density, this power density is started increasing, right? So this leakage power is a major hurdle. Now when we use a single core, now what people are trying to say, when we are using single core, the normalized energy will be like this. With the same energy, now you go down, operate at lower energy point, means at lower VDD, and make two cores. So with this, what problem we have solved? Problem of the power dissipation, static power dissipation particularly. So that is what people are trying to go with the dual core, octa-core kind of the processors. So this is the parallelism, is the one of the concepts which people are using it to solve this leakage problem. And when we see the bulk MOSFET, there are a lot of scaling challenges. So when we see the bulk, so when it was around 90 nanometer, the channel length was the issue. So they started using it, the kind of the devices, right? So this is the bulk MOSFET, right? So we do have the source, drain, gate, and as I told you, we started reducing LG. When we reduce LG, the device density will go up. But at the same time, short channel effects. Short channel effects means this was 10 micrometer, now it is 10 nanometer. The short channel effects like subthreshold slope. Another short channel effects is gate-induced barrier lowering, GI gate-induced gate leakage are go on increasing. And we try to reduce the VDD by fix the VTH. And when we reduce VTH, the IOP will go up. Similarly, if we reduce the junction, gate oxide thickness, the gate leakage current will go up. And whatever the solution we did for improving IOP, each has some pros and the cons. So the new transistor structure came up, what they think is, first of all, why don't you make is, first of all, ultra thin. Or ultra thin means this channel itself they are trying to reduce, right? This is the gate length and allows unity change that already we have seen. The leakage is the major hurdle. Now we make the thin device by lowering from this side. Then they make it intrinsic. Intrinsic means there will not be any doping. And after that, it come up with the SOI. That is silicon on insulator. This is the buried oxide. On top of it, we will have the gate, right? We'll take maybe break, then we will move further from the slide. So, I mean, in coming sessions, I will talk about this SOI and then show you the. I mean, now most of the tasks already I finished. I hope now. What my goal was, if I just started scrolling these sites now, and if he tell you something, you could not able to grasp. It will be very boring for you. So now I hope the fundamentals I told you. Now I just wanted to tell you why I am doing this. Right? Okay, we'll take a break. We'll meet again. And I will tell you now what will be the future challenges and what is happening in the technology. Okay.
Come back then.
Some more.
कुणाचा फोन आहे?
तुमचंच आहे.
नाही माझा तर फोन नाही आहे. मनोजचा आहे का? तू मनोजचा फोन आहे का मॅडम मागे? कुणाचा बाबा काय कुणाचा? मॅडम कॉलिंग होतो. हो का? नाही त्यांना सुचवा काढणार तर मॅडमची मॅडम
उद्या नाही ना?
आणि हा उद्या उद्या आहे. उद्या आहे आणि परवा ते ATAL इंडस्ट्रीचे
उद्या काय?
उद्या आहे आणि परवा ते असं
आत्ता बसल्या होत्या मॅडम. शिर्के मॅडम हा हे इकडे.
काय झालं?
काय तुमचे स्टुडंट्स आले पाठवते. काय माहिती हॉलिडे नाही महाराष्ट्रामध्ये दिली काय पाहिजे मॅडम.
सगळीकडेच.
म्हणजे आहे ते फील्ड फॉर्मॅट पाहिजे होता मॅडमला त्यांनी केला माझा मला जरा काय झालं असतं काही
त्यांनी हे केलेलं आहे आणि त्याच्यामध्ये मी काय
बडबड होईल पण ठीक आहे तो सेट करून आणि टेस्टचे मार्क्स पण लगेच स्पीक टेस्टचे मार्क्स स्पीक केल्यानंतर मग किती लोकांनी आणि मग ते समजत नाही पाठवून घातलं असं एका रस्त्याने भरलं तर ते टाकावंच लागेल मी भरल्याशिवाय तुम्हाला सर्टिफिकेट जनरेट होणार मी माझी पण आहे थँक्स लेटरवरती सांगते मग त्यांना दाखवून
खाली करू एक खाली करू start? So, I'll just so we're talking about this bulk MOSFET, right? So this bulk MOSFET has the scaling challenges, means reduce LG, the device density is good, but at the same time the short term effects will also increase, right? Then if we try to reduce the supply voltage and if we fix this Vg minus Vth, then Vth should go down, but once Vth will go down, the IOP will increase. Or if you fix the VGS minus IOP and VGS minus VTH is reduced, then IOP will reduce. So for bulk, there are some pros and the cons are there, and this is the simple expression which we have discussed why we are trying to improve this, right? So we want to increase the speed, so delay will have to reduce. So when we scale down this LG up to 90 nanometer, then there was no issue. But if you want to go below 90 nanometer, then there are different changes. We need to do short-term effects were large. So what people are trying to do, this IOP has to be reduced. So in order to reduce this, we try to reduce the VT and hence VDD as well. But the leakage occurs because of the short-term effects. So how to get rid of this? So in order to do this, we will reduce the thickness. Not only this, what people are trying to do is they make this as an intrinsic. So we will have the p-type substrate, they try to make it intrinsic. So why? Because if we have the intrinsic, there will be, because this doping is related to the depletion. Are you remembering this?
Yes.
If you want to increase the depletion width, what we are trying to do? Doping should be depletion width. If I wanted to increase, then doping should be low, right? If we increase the doping, depletion width will reduce. So this substantial slope leakage, that slope which I told in the IDVG characteristics, that we want to reduce. And that is limited by 80 by Q ln of C depletion by C ox. So C depletion we want to reduce. So C depletion means epsilon silicon by X depletion. C depletion means permittivity of silicon at the denominator will be depletion width. So C depletion if you want to reduce, depletion width you want to increase. Are you with me?
Yes.
So the depletion width if you want to increase, doping we need to reduce, and that is what doping will be reduced by making it intrinsic, no doping. So that is what people go for the intrinsic kind of the devices. Not only this another technology came, that is SOI, silicon on insulator, right? This is silicon on insulator. Insulator is buried oxide. So this is the SOI technology came, and these are the kind of the requirements which we need to do. So it doesn't mean that every time we will just focus on the speed improvement or the power reduction. It depends upon the kind of our electronic device which we have. If you see, let us say for example our cell phones, right? So what is the major requirement for the cell phones? We wanted low power. So low power means lowest leakage, low ion, and low ion, then high CVI, right, and high VDD. So if you look for the ITR, stands for International Technology Roadmap for Semiconductors. So as per ITR's requirements, what people are looking for, these servers or the CPUs, we wanted high performance. High performance is high speed. If you want high speed, we require highest level. Then we wanted lowest intrinsic gate delay, CG into VDD by IOR, right? This is CV high. So we wanted low. So that time we could compensate for high leakage. But if we are operating like low power CMOS, we wanted the low operation power. So low operation power means lowest VDD. And that time we could have the medium leakage. So as per ITRS, there are 3 circuit nodes: high performance CMOS, low standby, or low power. So depending upon that, we try to scale down our devices. And the major technology would be when we were around 205, when we talk about 90 nanometer, up to 205, people talk about the bulk CMOS. After 205, then people talk about SOI. Then up to 45 nanometer, people talk about bulk, then FDSOI. Then they come up with the higher technology nodes after 45 nanometer, double gate FinFET came. And now when we talk about today, these are up to 2020, we were talking about the FinFETs. And now we are talking about the gate around another devices in future technology nodes. So up to deca nanometer, this is around 10 nanometer, we were working on the FinFETs. But after deca nanometer, 7 nanometer or 4 nanometer or 3 nanometer, we need to look for the gate or around the transistors. So what will be the future devices? So if you see this was the planar around 2009 to 2011. This was the planar bulk MOSFETs, and the problem that time was the short term effects and the variability. Then we go with the SOI, then ultra thin body SOI. FDSOI means fully repeated SOI. Then after this we were talk about the double gate FinFET, and after this we have the challenges. So we need to go with the alternate materials, maybe germanium or maybe thermal semiconductors, or we need to look also for the device structures as well. So future devices will be nanowires, gate all around kind of the transistors. So these will be the future devices, and these are the technology innovations. So when we talk about CMOS scaling, then we do have the P-type FET, then FinFET, and these are the devices which are beyond CMOS. So when we look for the beyond CMOS, we